Welcome to this presentation on the evolution of AI capabilities. For years, we've relied on static benchmarks that test specific knowledge, but these don't tell us how useful an AI is for actual work. Today, we're discussing a more practical metric, the 50% task completion time horizon. Essentially, we're asking how long of a task can this AI handle before its chance of success drops to a coin flip. As of early 2025, we're seeing frontier AI models like Claude 3.7 Sonnet tackle tasks that would take a skilled human nearly an hour to complete. This isn't just about speed, it's about the reliability of autonomous execution over extended periods. By framing AI progress in terms of human work hours, we gain a much clearer picture of when these systems will be ready to automate complex, multi-step professional workflows. This new metric provides a continuous, intuitive comparison across vastly different model generations and capability levels. Let's now look at the astonishing pace of this progress. Following our introduction to the 50% task completion time horizon, we see that AI time horizons are doubling approximately every 7 months. This exponential growth is consistent across diverse tasks, from software engineering to cybersecurity. Since 2019, AI's autonomous task completion has surged from seconds to nearly an hour. This rapid scaling suggests that within 5 years, AI could automate tasks that currently take a human professional a full month. This is the Moore's law of AI autonomy, and it represents a fundamental shift in the potential for large-scale professional automation. But how do we actually measure this? Let's explore our methodology. So how do we actually measure this time horizon? It's a rigorous 3-step process. First, we built a diverse suite of 170 tasks ranging from 1-second code checks to 8-hour machine learning research projects. Second, we established a human baseline by having professionals complete these tasks, recording their time to complete. And finally, we used logistic regression to map the AI's success rate against the human time to complete, giving us a mathematical horizon point. This robust framework moves us past vibes-based evaluation and into hard empirical data that reflects the actual difficulty of the work being performed. This methodology is crucial for moving beyond the limitations of traditional benchmarks, which we'll discuss next. Building on our robust methodology, we recognize that the AI industry has a problem. Our benchmarks are getting too easy. Tests like MMLU, which once seemed impossible, are now being maxed out by every new AI model. But good at a test doesn't mean a model is good at a job. A real economic value comes from agency, the ability to take a goal, use tools, and solve a problem over several hours. This is why we've shifted our focus to domains like software engineering and ML research. These tasks are messy. They require the AI to handle unexpected errors and navigate complex file systems. By measuring the time horizon, we create a benchmark that doesn't saturate. As AI models get better, we just look at longer tasks. It's a ceiling-less way to track the true evolution of AI utility. This brings us to the underlying drivers of this progress: compute and forecasting. Why is this happening so fast? A big part of the answer is compute. We've seen that the amount of processing power used to train these AI models has been doubling at an even faster rate than the capabilities themselves, roughly every 3 to 4 months during the peak of the deep learning era. Our research links this massive investment in hardware directly to the expansion of the autonomous horizon. We're using frameworks like anchors to understand how much compute is needed to reach human-level performance on various tasks. The data suggests that as long as we keep scaling the hardware and refining the algorithms, the 7-month doubling of AI autonomy is likely to continue for the foreseeable future. This sustained growth is directly tied to the expansion of autonomous horizons. To make our findings reliable, we use 3 distinct task suites. This multi-tiered approach allows us to map AI capabilities comprehensively, from atomic actions to complex multi-day projects. First is HCAST, which is the bread and butter of our evaluation, covering 97 diverse software tasks. Then we have RE-Bench, which is the heavy lifter with 8-hour research projects that test the absolute limits of current AI. Finally, we have SWAA, or software atomic actions, which are the tiny split-second decisions that form the building blocks of larger tasks. By testing across all three tiers, we can see how an AI's ability to handle small details translates into its ability to manage large projects. Crucially, we made sure every single task was human solvable, so we're never asking the AI to do the impossible. Now let's consider how real-world complexity impacts these evaluations. One criticism of AI benchmarks is that they are too clean. In the real world, instructions are vague, tools break, and the environment changes. We call this messiness. We actually scored our tasks against 16 different messiness factors to see how they affected the AI. Unsurprisingly, AI models struggle more when things get messy. A task that takes 10 minutes in a clean environment might be impossible for an AI if the documentation is missing. But here's the key finding. Even on the messiest tasks, the models are still improving at that same exponential rate. This gives us high confidence in the external validity of our results, meaning these trends should hold up in the real, messy world of professional work. But how do we define real world in the first place? You can't say an AI is doing an hour's worth of work unless you know what a human can do in an hour. To get this right, we collected over 2,500 hours of data from human baseliners. These weren't just random people, they were high-level professionals from the world's top universities. We matched their screens and listened to their audio to make sure they were actually working and not just using AI to cheat. By taking the geometric mean of their successful attempts, we got a very accurate human time for every task. This is what allows us to say with mathematical certainty that an AI model has a specific time horizon. It's the most grounded comparison between human and machine effort ever conducted. This human baseline is crucial for understanding the AI's interaction with its environment. An AI model by itself is just a text generator. To do work, it needs a scaffold, a piece of software that lets it run code, read files, and see the results of its actions. We gave our AI models access to Python and Bash, the standard tools of the trade. What we found is that the secret sauce of the latest AI models isn't just knowing more, it's their ability to use these tools effectively over long periods. As tasks get longer, the chance of a model making a fatal mistake increases. Our data shows a very clear mathematical relationship here. As the human time to complete goes up, the AI success rate goes down exponentially. The frontier of AI research is now about making these tool use sequences more robust so that the AI can stay on track for hours at a time. This brings us to the mathematical decay of AI success. This slide shows the cliff that AI models eventually fall off. If you give an AI a 10-second task, it's almost 100% successful. But as that task stretches to 10 minutes, 30 minutes, or 2 hours, the success rate drops. For older AI models like GPT-3, that drop happened almost immediately. They were short horizon models. But for the latest AI models, that cliff has moved much further to the right. We found a near perfect correlation between the success rate and the logarithm of the task's duration. This is incredibly useful for forecasting. It means if we know how a model performs on a 5-minute task, we can predict with high accuracy how it will perform on a 50-minute task. We are moving from guessing to engineering. This brings us to the mathematical decay of AI success. In the real world, a 50% success rate usually isn't good enough. You wouldn't want a doctor or a bridge engineer who's only right half of the time. That's why we also look at the 80% horizon. There's a big gap here. An AI model might be able to handle a 1-hour task with a 50% chance of success, but if you need 80% reliability, it might only be able to handle a 15-minute task. This reliability gap is one of the biggest hurdles for AI deployment. However, the good news is that both metrics are improving at the same rate. The 80% horizon is also doubling every 7 months. So while we aren't at high reliability long-term autonomy yet, we are moving toward it at a very predictable and rapid pace. To wrap up, let's look at why these AI models are getting better. It's not just that they are smarter in a general sense. When we look at the actual transcripts of their work, we see 4 specific improvements. First, they are better at using tools. They don't just guess commands, they use them precisely. Second, they have better situational awareness. They know when they're stuck. Third, their logical reasoning has improved, allowing them to keep track of a complex plan over hundreds of steps. And finally, they are much better at error recovery. Older AI models would get into a death loop, repeating the same mistake forever. Modern AI models catch themselves, try something else, and eventually find a solution. These are the muscles of autonomy that are driving the exponential trends we've discussed today.